think maybe let me start to welcome our speaker. During that time, people will continue join. Okay, so good morning, everyone. So this is my pleasure again to welcome our EMSL Exchange speaker, Dr. Coty Jen from Carnegie Mellon University. So Dr. Jen is an associate professor in the Department of Chemical Engineering. And actually, I also went that during my master program. And also a board member of the Center for Atmospheric Particle Studies at the CMU. Jen obtained her PhD degree from University of Minnesota Twin City. And after that, she joined University of California, Berkeley for her postdoc training. And at the CMU, Dr. Jen's research is focusing on the atmospheric particles, chemical and physical chemical property, and also instrument development to provide the real-time measurement of particle. She also has a significant contribution, to our understanding of new particle formation. And today she will share her recent insight into the new particle formation. And let's welcome Jen again. And if you feel free to put down in the chat, so we will try to answer question at the end.
Perfect. Thank you for inviting me here. I've not been to PNL, but I know some of you through the 5 million meetings we seem to go to every year. If I'm a little slower, it's because I got in very late last night, and I will leave very, very early tomorrow morning. So this is a whirlwind tour, but I appreciate being here. So today I want to talk to you about new particle formation. It is a field I was in during my PhD, and then I left it because my PhD advisor told me there's no future in there. And then I decided he was wrong, so I came back. But all this work that you're going to see is not done by me. You probably heard this from most people. I literally just answer emails all day. It's like a very privileged lifestyle I have now. I really just go down to the lab and tell my students when they're doing something wrong. So it's a very, very fun job. But our work is primarily supported by NSF and DOE ASR. We also have funding from the Pennsylvania state government, and we partner a lot with Aerosydynamics, which is Suzanne Herring's. It's technically not her company anymore, but it's Suzanne Herring's former company for water CPCs. And just so we're all on the same page, I want to first give you a background of what aerosols are doing. And so aerosols come from all different sources. And when I say aerosols, I mean both particles and the gas phase, because that's the definition of aerosols. But we can see this image is from Jasper Kirkby. You can see that particles could come directly from like biomass burning or volcanoes, or can even come from industrial sources. So I'm from Pittsburgh. I didn't put two and two together, but Steelers, apparently the football team was named after the steel industry. Took me way longer to realize that than it should have. But there's a lot of industrial generated aerosols, both in the gas phase and the particle phase. And all of these primary emissions can go on and impact climate, but a lot of the gases that are emitted will react, transform into other things, and then can also form particles that go on and impact the climate. And so both secondary aerosols and primary aerosols will change cloud properties, with cloud property lifetimes, their brightness, or albedo, so on and so forth, all impacted by how big is the particle, the C particle to start with, what is the chemical composition, and how many there were. And these seem like simple questions. It feels like answering how many particles are there or how big the particles are feels easy, but it's really difficult. Getting reliable measurements in all the locations we need to constrain climate models has been extremely challenging. And so the primary focus of my talk will be on the secondary particles, because I do new particle formation. And so here's a graph that I took actually during my PhD, 2013, at SGP. And after that campaign, I promised myself I would never go back to SGP. And then I went back to SGP as a professor. So on the y-axis is particle mobility diameter, so how big is the particle? And on the x-axis is time of day. And so you see at some point around like 8 a.m., there's tiny little particles that are maybe showing up, but there's a lot of gas molecules there. The sun came up, is doing some photochemistry, converting like SO2 into sulfuric acid. It's heating up the earth, so it's causing ammonia to come off of the ground or from other sources. But at some early time when the sun comes up, there's a whole bunch of gas molecules that are waiting to do something. And then at some point, the concentration of them gets high enough, or their lifetime is slightly longer for whatever reason. They nucleate and they form these stable 1 nanometer clusters. And then you can see them with this particle size distribution. There's a really high concentration of these sub 2 nanometer particles. And after this point, they just grow. They grow via open question. It is heavily dependent on where the particle lives, what else is happening in that area. And so something that's interesting for this crowd is this classic banana plot was taken in 2013. This is an extremely fast growth rate. These grow from 2 nanometers to 20, 30 nanometers in the course of a few hours. If you go to SGP now, these growth rates are much, much slower. And things have changed in the last 10 years at SGP since this was taken. And so as the particles grow, they finally reach some size relevant diameters that they can then serve as seed particles for cloud nucleation. And so we can think of the life cycle of a secondary aerosol particle broken down to its like birth phase. So it's born, so nucleation, it grows, like it forms a toddler and then a teenager, and then like it's trying to be a productive member of society, which is around 50 nanometers. And at some point it activates, and that's when it sunsets and dies. It's very rough world being an aerosol particle. So this talk is primarily going to focus on that first stage, atmospheric nucleation. So why do gas molecules that are, very happy being gas molecules too, come together and form particles? And why do we care about atmospheric nucleation? So here's a famous paper from Gordon et al. And last time I gave this talk, it was much more. Gordon is actually my husband, so I can make fun of this paper all I want. But here's a climate simulation looking at what fraction of global seed particles come from a nucleation process, with the map of the world given here, and the redder the color means the higher the fraction of seed particles come from nucleation. And so if you look here, you get lots of red in the Arctic areas, all around the US, around Central Asia, Australia, around the Antarctic. And there's a lot of blue patches. And all the blue patches mean that the primary particles are the main source of CCN or seed particles for clouds. And so hopefully this makes sense. There's a lot of biomass burning in Western Africa. And there's a lot of anthropogenic activity in India and Southeast Asia. And in the Southern Ocean, it's thought that this is a large contribution of sea salt particles that go on to form clouds. And so caveat from the study is this climate model used an extremely simplified version of nucleation in the model. There is increasingly more and more evidence when people get enough funding to take a ship down here that a lot of the seed particles for clouds in the Southern Ocean are actually being driven by new particle formation processes. So if I can somehow convince Gordon here to rerun a simulation to include some of the more updated nucleation models, it should actually be redder. And so a lot of our cloud particles, a lot of these seed particles are driven by new particle formation. So if we have any hope of understanding how many particles there are, how big are the particles getting, we need to get the birth stage right. Like how can you predict like human growth if you can't even figure out how many people are being born, right? And so this is why we need to understand new particle formation. And so I'm not the first person doing this. This atmospheric nucleation has been studied over many, many decades. Here's a paper from PNAS, Chen et al., Pete McMurray's group, and they looked at the nucleation rate. So how quickly are particles nucleating per unit time versus sulfuric acid concentration. And over many, many decades of observations, they see that how fast particles are being formed correlates with sulfuric acid concentration. But it's not totally clear what that relationship is. So here's very polluted Mexico City compared to a very clean Jutila forest in the green dots, to Boulder, Colorado with a lot more anthropogenic like agricultural emissions, all put on this graph. So there's some correlation, but there's a huge spread. If I look at one sulfuric acid concentration, like 10 to the 6, we're talking 2, 3-ish orders of magnitude. And so it's not just sulfuric acid that's contributing to nucleation. There's other junk there that's helping sulfuric acid nucleate. And so that's another open question. If it's not just sulfuric acid, what other junk is there? And so there's been a huge push to try to model sulfuric acid nucleation or nucleation in general. And so here's kind of, I'm going to say the state of the art, but it's kind of bold. Model of looking at how particles form. So if we start with just monomers, we'll say, okay, sulfuric acid has to bump into something to form a monomer. And it forms a little tiny cluster like that. And the monomer can grow into a dimer. So it has two sulfuric acids and some other junk around it. And it can grow larger into a trimer, so on and so forth. So it can grow by each addition of a sulfuric acid or sulfuric acid plus junk, but it can also evaporate. It has these backward reactions here that allows it to fall back apart. So I could write down in very traditional chemical engineering ways, I can write down the production or the accumulation of a Gmer versus time is just the formation rate. So here's it being formed by two clusters colliding together and a big cluster evaporating. So here's its formation rate and its destruction rate. So the particle could get evaporated, it could hit a wall, or it could hit a bigger particle. So if I want to model nucleation rate, which is the left-hand side, mostly the left-hand side of that equation, I just need to know how fast is it forming and how fast is it disappearing. And so if I look at this equation, let's say for now, I can measure the concentrations of all these clusters. Everything in bracket, I can measure with the mass spec. That's pushing it. I'm like standing right in front of this. That's pushing it. Let's say we can do that. And then the next thing is the forward rate constants, these Ks. These Ks we're going to say is a gas collision rate of a molecule and a cluster coming together. For now, let's say we understand that. It's like, we'll go with hard sphere model. We're probably wrong within a factor of 2, but we'll take that as a win right now too. And so that leaves this kappa and this eta, and that's just lost to walls. Let's say we can also quantify that with the size distribution measurement or how much wall is there. And so all that's left in this equation are these evaporation rates. And these evaporation rates are heavily dependent on what is in your cluster. Like this cluster, which we call trimer, could have a couple of extra water molecules attached to it. It could have another ammonia attached to it. And every time the cluster composition changes, that evaporation rate, or how fast does that cluster fall apart, will also change. And in theory, I could ask my graduate student to go and measure the evaporation rate of every possible cluster out there. And they're feeling a little down right now. This would push them to quit. Like, there's so many combinations of cluster compositions out there. To be able to go and measure each and every one of them is not a good use of our resources or our time. And so because of that, it's led to this model being pretty inaccurate in modeling nucleation in the atmosphere. So the models are inaccurate and measuring it is inaccurate. So here's another size distribution plot. We have the diameter on the y-axis and time of day on the x-axis. And this was taken in Pittsburgh. This was a pretty clean day in Pittsburgh. I like it because it's a frowning face, which is kind of the general mood. And so at some time in the morning, we get a little nucleation event here, and then it grows and then it shrinks. And there's a lot of reasons for the upside down frowning face I'm not going to go into. But one thing I want you to get from this is it's extremely pixelated. And so we build our own SMPSs because we're poor. And because how the instrument is running, it creates these pixels. And so the instrument will scan through the sizes up this way, and it takes about 5 minutes to scan. But you can only scan through a certain size bin. And so that leads to this like pixel size bin that you have some limited information on. And so there's a lot that happens both in the vertical axes and the x-axes. In Pittsburgh, for all I know, a truck could have driven by in less than 5 minutes and totally changed the size distribution that would not have been captured in this scan. And also, we could talk about this later, is, nucleation happens on the orders of seconds, could happen on minutes. And so you could miss a lot with the traditional types of instrumentation that we use to measure the particle size distribution. So the models are not great and the instruments are not great. And so the whole goal of my group's research is first, how do we observe and model nucleation that happens in a chemically complex atmosphere? We are extremely good at making very clean measurements in the lab. Like, oh, let's take one compound and mix it with another compound. That's not how the atmosphere works. It's so gross. The atmosphere is disgusting, especially in Pittsburgh. So how do we model and observe nucleation in such a difficult environment? And then on top of that, sometimes you're lucky and your lab is in a very interesting place with really fun atmospheric chemistry, but by and far large, the particles we need to go measure are not convenient to measure. There's not like a 30 amp outlet just hanging out off the iceberg by your ship. So a huge portion of my group is trying to design more accurate, portable, and cheaper instruments to go measure the gases that help form these tiny particles. Okay, and so I'm going to take a deep breath. Like most people, we have a ton of projects happening in my group, and I will only talk about 2 of them. And normally I will poll the audience and ask which ones they want. But I think for where I am now, we should probably talk about my low-cost sulfuric acid instrument, because that's the one we've been putting on the TBS at SGP. Does anyone have any other thoughts? My group has also developed extremely fast, sensitive measurements of sub-3 nanometer particles. We call it the FARM. We were at SGP for a really long time. We also do detection efficiencies of condensation particle counters, a nucleation model for complex reacting atmosphere. We're moving more into understanding emissions from freshwater and marine environments. And so my students have been looking at emissions from harmful algal blooms to get us going, and then we're going to go to Maine this summer. And then some really surprising / disgusting results of sulfuric acid happening at night in Pittsburgh. So does anyone have a strong, sorry, people on Zoom, you don't get a choice. Does anyone in the room have a strong opinion on which of the other ones you would like to see? You don't care.
Somebody says the farm in the chat.
Farm, we can do farm. Let's do farm, fine. Zoom gets a vote. So we're gonna talk about 2 instruments. You're in a really heavy instrument place, so it kind of makes sense. Okay, so let's talk about the CPC to measure sulfuric acid. And so I've been fortunate that my husband is a climate modeler, and I told him, this was before the pandemic, I'm like, I'm pretty sure I can retire. I came up with this cool model for nucleation, I'm done. He's like, no, you think you have it covered. Our models can't even get sulfuric acid concentration right. And I said, how's that even possible? Like, what good is your model? I asked that question to him a lot. And so I looked into it some more, and I was trying to figure out why are climate models getting sulfuric acid concentration right. Sulfuric acid isn't just important for new particle formation. It is important for particle acidity, is important for most particle phase chemistry. It's important for the pH. It's important. And so the way climate models do it is they first predict how much SO2 is emitted. It uses emission inventories, and it will use the emission inventories to extrapolate how much SO2 is in a specific location. So here's an example of the UK Met Office climate model that compared the ATOM measurements of SO2 to what the model was predicting. So the measurements are given in black, and the model is given in blue. And so the paper conclusion was, okay, the model is doing a pretty good job for SO2 predictions across different latitudes and across different altitudes. And I looked at this and said, sometimes it's getting it right. Sometimes it's up to an order of magnitude wrong, but by and large, it's about a factor of 2 to 4 wrong. And so, okay, getting it right is a factor of 2 to 4 wrong. But that's just SO2. SO2 is just a precursor for sulfuric acid. And so in order to convert SO2 concentration to predicted sulfuric acid concentration, climate models use something called proxy relationships. And a proxy relationship is basically someone went somewhere and they measured SO2 and they measured sulfuric acid and they correlated it. And so every location someone has done a measurement, there's a different proxy relationship. And so a climate model is pulling all these different proxy relationships and hoping they can be interpolated between locations. So that's, from a measurement perspective, a little sketchy. And so these proxy relationships often go to sulfuric acid to the SO2 to some power. And the power ranges between like 0.4 to 1.1. I've seen it go as high as like 2 to 3. So if you take your factor 2 wrong SO2 concentration here, it's now getting scaled by, up to a factor of 2. And so on top of that, once you have a predicted sulfuric acid concentration, you want to convert it to a nucleation rate. Typically, they also use proxy relationships. They say the nucleation rate will scale to the sulfuric acid to the power of 2 to 3. So the uncertainty of SO2 is now being propagated with each of these increasing exponentials. And so getting SO2 wrong and getting sulfuric acid wrong is pretty critical and quite detrimental to a lot of these climate models. And so this was kind of a bet we do over the dinner table. He kind of bet me, challenged me, like, can you take sulfuric acid measurements all around the world? And I laughed, no. And I'm like, wait, but I think I can design a better instrument to do this. And so right now, to measure sulfuric acid at the atmospheric concentration levels, you have to haul a giant mass spectrometer that you love dearly to SGP, and you have to take these measurements. So this is a chemicalized atmospheric pressure chemicalization time of flight mass spectrometer. I asked my group to send me the most disgusting picture they could find of it, and this is how it normally looks. So they them cleaning it up didn't even make it look better. But it's a difficult instrument. You have a lot of really awesome mass spectrometers here, so you have a lot of experience, how much power they need, how even if you think about moving them, they break. You look at them, they break. You go on lunch break, they break. So they're a pain to operate. And they're also extremely expensive. This one that people take in the field probably range between $300 to tariffs, probably $600,000 now. So to deploy these at high spatial resolutions is also not possible. Not only because of the weight and the power, but it's just too expensive. And so because of that problem, we have very limited measurements of sulfuric acid. We will bring our instrument to SGP, we'll park it there for 6 weeks, and then we leave. And so there's no long-term measurement of sulfuric acid in places we need it. So the goal for this study is how can we develop a more compact, more affordable measurement technique for sulfuric acid. And the way we're going to do this is we're going to leverage how sulfuric acid nucleates in the atmosphere and then make that happen for an instrument. And so the way sulfuric acid nucleates in the atmosphere is the sulfuric acid molecule will bump into an atmospheric base, like ammonia or dimethylamine. If it bumps into dimethylamine, it actually does not really evaporate. It just happily forms a cluster, and that cluster will grow from a monomer, will collide with another monomer to form a dimer, trimer, and tetramer. So it'll just grow bigger and bigger and bigger. And so if this happens, in theory, you can write down all those cluster balance equations I showed you before, and then we can actually do some back calculation. If we knew the concentration of dimethylamine, and we knew the concentration of measurable 1 nanometer particles in a set amount of nucleation time, we can actually back calculate the sulfuric acid. And so this is basically trying to use what's happening outside, and we're constraining it into a controlled reactor, so a particle counter can now count a converted sulfuric acid molecule. And so we call this instrument the sulfuric acid dimethylamine reactive condensation particle counter. This was made in the pandemic, so it's called the SATR CPC. And the next generation is called SATIST. We worked so hard to get that acronym working. But basically, we take sample sulfuric acid and we mix it with an extremely high concentration of dimethylamine vapor. It is so high that it's not the limiting reagent. It is so high that even if its concentration varies, we don't even care. And so those two compounds will react, and we'll count it with a 1 nanometer CPC. In this case, we're using a diethylene glycol CPC, but we've now converted to a water CPC because it's actually much easier to use. But we know how long it takes for the reaction to occur in this reactor, so we count how many particles, and then we back calculate the sulfuric acid. We ran all these laboratory experiments at ranges of relative humidity, at room temperature, and those are the rest of the parameters. And so here's the comparison we did in the lab. We put sulfuric acid vapor into nitrogen, and we measured it with our SATR CPC on the y-axis, and our sulfuric acid concentration measured by what we call the standard, which is the SIMS. It's not a great standard technique. The SIMS has a lot of problems. And so comparing two uncertain instruments is the best we can do right now. And so if you look at this graph, there is broad agreement between the two instruments. It's not perfect agreement, but there's agreement. And we think a lot of the spread is not because of the SATR. We think it's because our mass spec was doing its own thing. And so this is, okay, it gave us hope. This seems to work in nitrogen, but unfortunately, sulfuric acid never just happily lives in nitrogen. We thought, okay, we need to give it more realistic gross air to see if this works. And I said, what is the grossest air we can think of? And it was Pittsburgh room air. And so we stripped all the particles out of the room air and we put sulfuric acid in, and then we fed it into our two instruments, and we get these orange dots here. So slightly lower than what we were seeing in nitrogen. And we actually think, again, this sounds like a cop-out, I'm sorry. We actually don't think it's the Saturn CPC. We saw some very bizarre things happening with the SIMS reagent ion when it was sampling room air. We think there's some junk in the room air that's combining with the reagent ion that's stopping it from ionizing things we need it to ionize. That's our best guess, but this is something we broadly see with the SIMS whenever we do this. The Saturn measurements for that specific sulfuric acid source, which is pretty constant, seem to measure exactly what we thought it should be measuring. So now it seems to work. I'm not saying it works perfectly. It seems to work in the lab. The next thing we want to study is its dependence on relative humidity. We're going to take this instrument to SGP, and unfortunately, SGP is not a nice 40% RH. It's like 100% all the time. So my group looked at changing the relative humidity from like 7% up to 80 some percent. And it's color coded here based on relative humidity. We see no clear dependency of RH. Maybe there's a slight one, but not more than any of the other uncertainties of the instrument. So this is great. Seems to work in the lab. Now we need to work outside. And the problem with lab measurements and outdoor measurements is outside there's also annoying particles. And so if we're just counting particles with a CPC, we won't be able to tell the difference between a 1 nanometer particle that's formed in our reactor here. So we can't tell the difference between a particle we're trying to form and a pre-existing particle that's just hanging out outside. So how can we differentiate these two? Given the limited time constraints before we had to deploy, we took a very brute force approach, is we literally just built another instrument and we called it the blanker. And so instead of pumping in dimethylamine, we just put in particle-free clean air. And so we will take literally what particle concentration measured by the Saturn and subtract it by the background measured by the blanker. Extremely brute force approach. Fortunately, our setups are really small, so both of them fit on the TBS. We're thinking of better ways of doing this, and I could talk about this after the fact if you're interested. But we have a second generation coming. It's called the SATIS, where we don't really need the blanker as much. So we went to SGP in May last year. We went middle of May all the way through June, and we got to put our instrument on the TBS. And I think the best thing that came out of this campaign were the photos. It was like 110, 115 degrees Fahrenheit there. It was very hot. It was so hot, almost all of our TBS flights were done at night. And the weather was awful. And we put our Saturn blanker onto the TBS. So here's either the Saturn or blanker. I think this is probably the blanker and this one's the Saturn, along with a lot of the other standard TBS instruments. And it was sent up. And a couple of times the wind caught the balloon and slammed it to the ground. CPCs kept working. If it were a mass spec, the mass spec would have been broken. Here's it. Again, we do a lot of night flights. So here's it dawn. I'm so glad I got to stay home and just sleep, and my student had to deal with this. Okay, so here's what we measured as we went up on the TBS. Here's the Saturn blanker measurement in the early morning before it was on the TBS. So this is just surface level. And the two instruments agree almost perfectly. If they don't agree perfectly, there's something wrong with our measurement technique, and then background subtraction would not work. So we're very confident our instruments were working. And they went on to the TBS. So here's what the SIMS was measuring for sulfuric acid concentration. Here's what the Saturn CPC measured for sulfuric acid concentration. That was background subtracted by the blanker. So the Saturn CPC is a little bit, it's about a factor or two higher than the SIMS. It's squigglier than the SIMS. The color scale on the Saturn points here indicate the altitude. We don't, like the Raspberry Pi checked out there, so the battery died. You win some, you lose some of the TBS measurements. And so not perfect agreement, factor or two, but it is capturing the right trends we are seeing on the ground. There's a lot of reasons they might not match because, again, we are up to, a few hundred meters above the surface level. The squiggliness is probably because the CPC was just spinning. And we did not test for spinning CPC in the lab, so we don't know how to correct for spinning. And also, it was like 110 degrees Fahrenheit. that CPC was very pissed off at us. It's not supposed to be operated at those temperatures. So it just like couldn't reach the temperatures it needed. So we think a lot of the discrepancy is because of those. But we think it's working past all that. And so our plan is to continue to prove on this, and we're actually going to be deploying the SATR CPC across Pittsburgh. We are fortunate enough that we have like 21 nanometer CPCs now, so we can build 10 of these. My lab flooded, so like insurance has bought me all these new toys to make me feel better about my life. So that's the end of this study. We can take questions at the end. And fortunately, the next thing that Zoom wanted is the CPC farm. And so here's a graphic from Sam O'Donnell that came from Jeff Pierce's group, looking at new particle formation. New particle formation traditionally has been measured at ground level. But a lot of folks are saying in the field is it's very possible that as the mixed layer, or as the boundary layer is expanding, it's bringing up a lot of precursor gases up into the atmosphere where it's cleaner and there's not that many particles. And that gives these precursor gases a chance to nucleate and form these tiny particles, which then are vertically mixed down that we then measure at the surface. And so we think we see hints of that in our particle size distribution. But the problem is those processes occur really fast. Vertical mixing could happen on the order of tens of seconds. It could happen on minutes. So how do we capture that in our size distribution? And so here's the traditional instrument. This is the same one I showed you before. We have about 5-minute time resolution. And something else you can see here is if I want to capture nucleation, I need the size distribution from the 1 to 3 nanometer range. That's where particles are being formed. And if I look at this, it looks like the SMPS cannot measure there. And this is, I mean, we're pretty good with particle instruments. This is the best we can do with the commercially built instruments. And so if we can't push a commercial instrument down there, most people can. And so the reason why SMPSs really struggle is they just have very poor sensitivity in the sub 3 nanometer size range. So let's take an SMPS. It's composed of tubing, a neutralizer, more tubing, a mobility analyzer, and a condensation particle counter. Each of these pieces contribute to the poor sensitivity. And so you have diffusion losses in the tube. 3 nanometer particles, all they want to do is stick to walls, I swear. They just diffuse and stick to walls. And you have a neutralizer and then more tubing. The largest losses will happen in the neutralizer. It is almost impossible to get a charge onto a sub 3 nanometer particle. You get less than 1% of your total particles population will get a charge from a neutralizer. So most of your things will disappear just from the neutralizer. And you have more tubing, and then you have a mobility analyzer. The diffusion losses of a 1 nanometer particle in the mobility analyzer is about 94, 95%. So of that 1-ish% that got charged, you're now losing 95% of that 1%. And then you make it to a CPC, which has some detection efficiency curve. So you're probably going to lose another 50 to 90% there. So here is the noise threshold of an SMPS. If you're trying to target 1 to 3 nanometer particles, you need roughly 1 million, 10 to the 5, 10 to the 6 number per cc. This is a DND log D plus, so slightly less than that in concentration. You need a ton just for your CPC to count a particle. So the sensitivity is really, really bad. So the question I asked is, can we do better than this? And because we're a very brute force group, and we apparently have tons of condensation particle counters, we built something known as a condensation particle counter for atmospheric rapid measurements. We forced that acronym because we were SGP and it was a farm. So what it is it's no different than a CPC battery. So this is 5 CPCs, and now it's about to be 20 CPCs. Actually, right now it's 10. We're about to get 10 more. But each CPC is parked at a different cut point. So the first CPC can see 1.4 nanometer particles and bigger. The next CPC can see 1.6 nanometer particles and bigger, so on and so forth. So we have 5 CPCs, each parked at a different cut point. And the cut point is determined by the temperature of the growth tube. And so we always keep the conditioner at 1 degree Celsius, and we vary the initiator temperature from 42 to 98 degrees Celsius to change this cut point. So 98 gives us the smallest cut point of about 1.4, and then 42 gives us about a cut point of 2.8. And then after that, there's a moderating stage, so you don't get a ton of water in the optics head. And then we keep our optics head about 35 degrees Celsius. And so we have 5 of these. Oh, and here's what I mean when I say detection efficiency. So on the y-axis is the fraction of particles we can measure as a function of the diameter of the particle on the x-axis. So at 198 temperature difference, we see about 50%-ish of 1.4 nanometer particles. And so as we change the temperature, this curve will shift to larger and larger sizes. And so the easiest thing to do is when you have a CPC battery to find the size distribution is we'll straight up take the difference between the 2 bins and we will divide it by the log of the diameter difference. And so when we did that, we thought, okay, we should probably simulate this before we actually do some measurements. So we did a simulation where the input simulated distribution is given in the dotted lines. And here's what the CPC farm would measure based on that simulation. And if we took those theoretical measurement points and we inverted it back into the size distribution, we get those square points there. So it's not a great match. And we thought the reason why it's not so great is because these are imperfect detection efficiency curves. They're not like you see nothing and then you see 100% as the diameter increases. Some of these CPC channels will see some of the particles that it shouldn't be seeing, and so on and so forth, because there's a slight slope to these curves. And so if we take those curves into account, we did a matrix inversion. And so if we did that, we actually get the red bars there. So we get a much better agreement when we're taking this into account. So here's what it looks like when we did the measurement. This is in Pittsburgh. And so we get this is an SMPS measurement, diameter on the y-axis, time of day on the x-axis, and you get a nice banana plot. And you see the pixels, and that's like the 5-minute time resolution right there. And here's what the CPC farm is seeing in the 1 to 3 nanometer size range. So this should live up here if we combine them. The first thing you should notice is the width of the lines on the CPC farm are extremely thin. We get about 1 second resolution when we're taking the measurements with the CPC farm. Way better than the 5-minute scans. And the next thing you should see is the CPC farm has way better sensitivity. Like we can see stuff here that isn't even measured with the SMPS. And so if I'm trying to measure how quickly particles are being formed with an SMPS, I am missing the actual nucleation event. This event starts slightly before than what the SMPS is seeing. It's occurring at a much higher intensity than what the SMPS is seeing. So the nucleation rate we calculate with the CPC farm is usually orders of magnitude higher than what an SMPS sees. And that is, I mean, if you're trying to model nucleation rate and you're given the wrong observations, you have no chance of getting the model right. Okay, so we get better time resolution, we get better scans, and here again is the emphasis of that's where our CPC farm size distribution lives. It lives in the sparse whiteness that's actually not that white and not that sparse. And there's a lot of fun things that are happening during this time period. So we see the obvious nucleation event. And the next thing to look at is if we took the ratio between these, there's all different points here that aren't occurring here. But it seems like maybe they do occasionally match up. So we looked at that. And so here's a vertical slice up this contour plot. And here's what the I have faith. I stepped on wire. It's really well the higher size bins of the SMPS. And this is just noise of the SMPS. It's just giving you just random noise, which is extremely high. And sometimes the CPC farm sees something higher than what is detected by the SMPS, and we believe this is also just random noise. And if we take another time slice, we see that sometimes they agree. And this is always the case with noise. Sometimes it works, sometimes it's too high, sometimes it agrees, right? And so the reliability and sensitivity of the CPC farm is way, way better than the SMPS. And so we're actually expanding. This was us at SGP. So we have water CPCs. We have also done a whole bunch of butanol CPCs. And because, again, my lab flooded, so all these instruments are toast, we are getting 20 CPCs. that are going to be switched between an alcohol-based and a water-based one, so we can get some more composition dependence on the sub 3 nanometer particles. So this is what it looked like at SGP, but again, it's rapidly changing because lab flood. Okay, so, oh yeah, my student labeled all these. Okay, so I just want to go to my conclusion slide because it's probably super long already. Sorry, there's a ton of slides in here and I never know how many there are. Okay, there. Okay, so my group focuses primarily on where do gases of new particle formation come from? How do they react, and what particles do they make? And we have a whole variety of really fun projects happening right now. And I'm happy to talk about any of these in later. But here's my amazing group. We have one new member who's not in this picture, Milena. We only take one picture per year. We don't have great time resolution, so we miss a member every so often. Most of the results I showed today, Dom, who is long hair now, is the primary person pushing, making the SATR CPC. And then Darren, who thinks he's cool sitting on the railing there, is the one primarily doing the CPC farm. And they are graduating soon, and I will definitely miss them. But a whole bunch of Joy and Zizi are the ones taking over. So if you have any questions, I would be happy to answer them. Shoelaces inside this whole time.
So for online folks, you can raise your hand and unmute for question. And first, any question from the room?
Yeah.
So for your CPC farm, how you characterize them to make sure they're performed equally? Like say, if you have one active 1.4, 1.6, but does this 1.6 also can activate can run at 1.4?
Yeah. So the first thing is we measure the detection efficiency curve. So we do that before, we do it after the campaign. It actually shockingly does not vary. It doesn't matter, my students sometimes make a bad wick. Sometimes there's dirt on the grow tube and it seems to not change the detection efficiency curve. It's really just sensitive to the temperature. And obviously if the wick can't hold water, then that's bad. The other thing that we were very concerned about is we had to make sure all the instruments agree. If they're all set to the same temperature, they should all read exactly the same number of particles. So during the field, we don't dynamically change the temperature to set them all the same. Actually, we do that once a week. But actually, there's a lot of periods, especially SGP, where there's no sub-10 nanometer particles. It is just happily hanging out. The mode is hanging out at 50 and there's nothing tiny. And so we use those periods to basically correct for any kind of instrument drift. And so they will all line up within 50 to 100 particles per cc. It's pretty amazing. And so we run, however long that those very clean events happen, is the correction factor we will apply on that CPC to get it to reach the average concentration, if that makes sense. So because we're taking the difference, we are extremely sensitive to slight drifts. And so we've developed all these techniques to try to correct for it. We're hoping the next deployment, we will not do atmospheric sampling. We'll actually just generate ammonium sulfate at 50 nanometers for 5 minutes and make sure all the instruments will line up. Yeah. Does that answer? Hopefully.
Yeah. Well, the following. Well,
You can go. Then manage.
okay, let them go first.
Okay. Hi, Coty. Very nice presentation. I have several questions, but I will just think about the most important ones. I was confused, first of all, why the blank? Why did you expect the blank and the SAD technique to line up exactly? Because especially on the tethered balloon system.
Here, this slide. Yeah.
Yeah.
So
yeah, go ahead.
Yeah, so if there were sulfuric acid hanging around at a high enough concentration, the SATR would see high, more particles in the background. What we wanted to do here, this was actually, this was before the SIMS was picking up a high enough concentration of sulfuric acid. So really the SATR should have not nucleated any particles. So both instruments, the SATR and the blanker, should have just measured exactly the same number. Does that make sense?
Okay. Yeah. Sounds good.
And again, because we're
then
doing, sorry.
Go ahead. Sorry.
Well, because we're also doing a difference between two CPCs, we are constantly paying attention to if our two instruments match up. Because any drift in them will totally screw up our measurement. So.
Okay. And then the second question I have is again on the right-hand side panel here.
Mhm.
When do you, because it seems that the SIMS instrument has its own issues, right? Even in the lab, if you had something interfering with the reagent ion, you had some drifts in the SIMS. And in the real world, there could be other issues which are not characterized, right? You have a bunch of different chemicals that may be interfering with the SIMS.
Mhm.
So this comparison, like how would you say when the SIMS is more reliable compared to when the SAD-R CPC is more reliable in
That's
the real
rough.
world?
That's a rough question, Manish. So I have a student working on a paper now where she's comparing two different versions of SIMS. They have very different inlets and how they measure sulfuric acid. And even those two SIMS at SGP measuring, I guess they weren't measuring from the same wall. They were measuring like around the corner from each other, are still about a factor or two off. So I don't have a good answer for you other than it's all, I think when we as a community, we blanket say we're all within a factor or two. That's probably still the best we can do. And like all this research being put into the SIMS measurements has just to uncover the reasons why it's a factor of two. But I know it's not a satisfying answer, but it's just, we don't know which one's better. My students prefer to use the SAD-R CPC because it's not a pain to work with, but it's probably within the same uncertainty levels as the SIMS.
I think that's a great thing to know. And also, I think the real value of it is also when you mount it on a tethered balloon system. And if you can go below 3 nanometer particles, at least you can tell where it's nucleating in situ, right? Because
Yeah, we were actually, Chongai Kwan came on the campaign, the second half of the TBS campaign. So this measurement was before Chongai showed up with his two CPCs. So we had 4 CPCs on the TBS. No, we had 3 he only brought one of his, but we had 3 CPCs. So we have the sub-10 nanometer particle concentrations. What we were realizing is something I did not have time to make slides for because we're just analyzing the SGP data now, is a lot of times as the TBS is going up, we think, oh, it suddenly sees a whole bunch of tiny particles. It's because it's forming a loft. We actually see something happening similar at the surface. So I think the TBS doesn't, basically ideally you want to park 100 TBSs at every altitude to capture the fast dynamics. And so there's a lot that we're trying to interpret from our TBS. Like, so if you look here, there's a slight time delay in when these start to go up. And we don't know if that's because, the wind was a little bit different or the instrument was like, there's a lot we don't know. And it's because the TBS can only move at a certain pace. So.
While we're on this slide, you talk about the uncertainties of the instruments, but I guess could you tell me whether you think it's realistic to expect that sulfuric acid would be higher aloft at the surface? Because I'm assuming this is a fast reacting species. So, and I'm assuming that this is in the convective boundary layer. So maybe convective boundary layer is generally well mixed, but it's well mixed for slow species. But for fast species, maybe you do have a vertical gradient. And so, as someone that's not an instrument person, but that's more a modeler, what am I to believe, I guess, right? Because I could be convinced that there should be a vertical gradient in the atmosphere, and having information on that. It could be that SO2 is being transported into the free troposphere and then trained into the top layer, and that's what you're seeing here.
Yeah, I don't know.
Yeah.
From our measurement, our measurement only gave us a snapshot of like what happened at that moment, and we don't have. Ideally, to get all this, you just need a ton of these instruments located everywhere. Something that I did not talk about that kind of gets to what you're asking. So a problem we're seeing in Pittsburgh is we see a ton of sulfuric acid forming at night, like more sulfuric acid at night than we see during the day. And so it is very possible for sulfuric acid to be formed in like weird ways that, you know, aren't being captured by models too. It could be transported, it could be formed. It's hard. Sulfuric acid, SGP has a longer lifetime because there's just not that many particles. We're talking tens of minutes instead of Pittsburgh, which is like a minute. So I don't expect sulfuric acid to get transported super far unless there's something like a really fast wind velocity that's pushing it around. But my guess is it's forming, and it's just like SO2 was transported from somewhere there. But it's the best we can do.
So I was wondering how fast are those, I mean, you showed the plot, I'm just trying to get the y-axis, that how fast that your 1 nanometer particle is getting into a 3 nanometer particle. So I'm wondering if that's something, if you have a longer time duration, and if that happens, that you forming those particles but not going to the growth stage, and you see like a snapshot of those events that are at the nucleation stage, but not kind of getting into the growth stage.
Yeah, so for the Satyr specifically, we don't give them that much time to react. We purposely clamp down the reaction time so they don't grow bigger.
I'm not talking about the farms.
Oh yeah, about the farm. Okay. So you're asking how does it grow from like 1 to 3, and if we're just kind of
long?
It totally. So, I mean, like we're in Pittsburgh, so these things like I don't. I should just memorize the slide numbers. So if you look here, it looks like there's not really growth. It's just like they form. And there's like a distribution of them forming. But it's possible, I mean, for something to grow from a molecule to like 2 nanometers, not quite 3 nanometers, we're talking like 10 seconds. It's really fast. And so it is possible there is growth in those vertical slices, even at 1 second resolution. It's just hard to capture. Like they just grow really fast. And so there's something a bit, right now we're working really hard to resolve the smallest bin, because the smallest bin is not 1.4 nanometers. We actually think it's measuring a single sulfuric acid molecule up to 1.4 nanometers. So I think once we can resolve that, we will be able to see the growth through the 1 second scans a lot better. But they can grow really fast in cities. There's just too much junk, and they just like happily do their own thing. But I mean, sulfuric acid concentrations in Pittsburgh are like mid 10 to the 7. And so that's plenty of sulfuric acid to get them grow really fast. SGP, we didn't, I wish I have the slides. SGP is really different for the farm. We don't see these 2 bins. We only see the top bins with a bunch of particles. And this is another reason why we think it's happening aloft and is blowing towards the surface, because we don't see nucleation at the smallest bins. They're already bigger. So it's like bringing precursors down that are happily reacting as they come down. And so, yeah, that's a different story. Yeah.
And this one was not on the TBS, this one on the ground.
I could put my CPC with that. Actually, I bet it could fit. I bet it could fit 5. Maybe.
Nothing else.
but nothing else. Yeah. I think the water CPCs, because they need to reach 99 degrees Celsius, the power requirements are high. And so yeah, we're working on it. We have a plan with ADI. Yeah, we just have too many CPCs, but yeah. Everyone lost TPS measurements.
Any questions from online at the room?
Yes, I'm curious, like a general question, do you know the lifetime of an SO2?
Lifetime of just SO2 or sulfuric acid? I don't know for SO2 off the top of my head, for like Pittsburgh or something, but sulfuric acid is really, really short. Like, yeah, it's like a minute in Pittsburgh and like tens of minutes in SGP. It's mostly lost just by pre-existing particles. So if you have just more junk, like this stuff up here will really depress the lifetime of sulfuric acid because it just gets stuck to it. And so the study I did talk about when we measured sulfuric acid at night in Pittsburgh, it has a crazy high condensation sink, so its lifetime should be like nothing, but we still see it being formed. So sulfuric acid is weird, but I don't think I answered your question. I just gave you perfect.
Okay, but it's split probably within minutes.
SO2?
Mhm.
Bit longer, but it's also not very long.
Mhm.
Yeah, because it can also go into like droplets and things like that.
There's a question, maybe Zena wants to bounce off of that.
Yeah, so quick question. Hi, I'm Zena. Great talk. I think you may have already said this, but I might have missed it. So the CPC farm is on the tethered balloon or it's not?
No, it's not.
Okay. Are there any plans or any possibility for the CPC farm to be on like an aircraft or something like unmanned in the future?
I mean, if someone funds me, yes. We
Okay.
would love to do that. That is the goal. Same with the Saturn. It is like we are building things that are like more compact and deployable. The CPC farm can actually get quite small if we put our mind to it. And it's actually better suited for airplanes because we're not so much power limited as much. And these are
Right.
not power intense instruments. Just connecting them to a battery on a TBS is just not great. So we would love to do that, but everything is just like funding limited. So if someone's interested in doing this, we're happy to do it.
Right. Yeah, that's good to know. We had a project at the SGP with the Arctic Shark, the unmanned crewed system. So maybe we can chat offline.
Yeah, because I remember the Arctic Shark was there in May when we were there as well.
Mm-hmm.
And I was like meaning to email Gannett about it. And then like 2025 happened. And
Right.
just for
Cool.
the
Thank you.
background, my lab flooded like mid-January and everything is toast in my lab. So like my whole life has been consumed by getting my lab back online. So
I remember I keep getting like from the alert, the CME, but it never happened. Professors keep telling us that don't ignore that can happen.
this is the second time my lab has catastrophically flooded. And so my new career goal is to make waterproof instruments. I think that'd be great. Yes. And then I asked our facilities people what we can do, and they're like, could you put umbrellas over your instrument? I'm like, not a helpful suggestion.
Last call for questions. Any questions? Okay, then let's thank our speaker again. If we